Hello students, welcome back to Engineers Academy. Today in this video we are going to discuss this particular problem 349. We have already solved this problem in the previous video, but now the problem has changed a bit, and now the problem says that for the davit of problem 349, determine the largest allowable distance x when the tension in line ABD is 60 pounds. So now in the previous problem we were given the moment about the z, the magnitude of the moment about the z due to the resultant of the force at A, 279 pound-feet, and we were asked to find the largest allowable tension when x is equal to 6 feet. Now we are given the allowable tension, we are given the tension in the rope is 60 pounds, and we are asked to find this x value. So now as we know that the moment about point C will be the cross product of RAC with the resultant of with the resultant at point A. So the resultant will be, as we know from the previous problem and problem 322, that the resultant will be, if we cut these ropes, then the resultant is equal to the vector sum of these two forces plus this. So let's say that these, if I cut these three ropes, if I cut these three ropes here, so we will have two forces acting vertically downward. So we will have two forces. Let's say these two forces are TAB. So let me show that here we have two forces acting vertically downward, and these are TAB. So we have two. So this is 2 TAB, and these are vectors. And similarly from A to D, we will have TAD tension in the rope. So the resultant force at A will be equal to 2 TAB, the vector sum of 2 TAB plus TAD. And similarly, since we are given the moment about the z-axis, so we have to find the allowable distance x for that moment about the z-axis. So we need to write the moment about that z-axis as well. So the moment about point C, as we know that the moment about point C will be the cross product of the position vector of A relative to C with the resultant at the resultant force which is acting at point A. So this will be the moment about point C, RAC cross product with RA, and since we are given the moment about that z-axis, so if we write, if we take the dot product of this moment with the unit vector along the z-axis, that will give us the z component of the moment about point C. So we can say, and that will give us the magnitude of the moment, the z component of the moment that is acting at point C. So this is the magnitude. So that magnitude is equal to the dot product along the z-axis, the unit vector along the z-axis, which is k, with this mc vector. And this will always give us, since this is the dot product, this will always give us the magnitude of the moment about the z-axis. If we take the dot product of this moment about point C with the I unit vector, if we write it like this, I dot mc, then this will give us the component of the moment about point C along the x-axis. If we take the dot product of the j, then we will get the y component of the moment about point C. Since we are interested in the z component of the moment about point C, we will take the dot product of this with the unit vector along the z-axis. So this is k dot mc vector, and this will give us the scalar value that will give us the moment about the z magnitude. So since we know that mc is this, so we can further say that k dot, we can say that k dot this is that mc. Now we need to find this in terms of ij and k, and we need to find ra in terms of ij and k. So now we know ra, which is the vector sum of these three forces, so 2 tab plus tad. Now tab is 60 times the unit vector from A to B, and the unit vector from A to B is the unit vector along the negative y. So we can say that TAB is equal to 60, since the magnitude in this whole cable is 60. So we can say that TAB is 60 along the negative j. So minus 60j. So TAB is minus 60j, and since we want to find 2 TAB, so 2 times minus 60 is minus 120. So this is 2 TAB minus 120j. Similarly, TAD will be equal to, we can say that TAD will be equal to 60, since the magnitude of the tension in the cable in the wire is 60 times the unit vector from A to D. And the unit vector from A to D will be the position vector from A to B. We can say that 60, and the position vector from A to B divided by the magnitude of that position vector. So here you guys can see that this is 60, the magnitude, and this is the position vector from A to B, and this is the magnitude of that position vector. So now the position vector from A to D, sorry, this is A to D, right? We are going to find TAD. So the position vector from A to D divided by the magnitude of the position vector from A to D. So now we can find the position vector from A to D if we start from A and we start moving towards D along the x, y, and z axis. So from A, if I travel 3 feet in the negative z, so that will be minus 3k, and then I will travel 7.75 feet in the negative y, this is the positive y, so we need to travel 7.75 in the negative j, so minus 3k minus 7.75j, I will reach here, and then from here I need to travel x feet distance in the positive I. So x feet distance in the positive I. Now the magnitude of this will be x square plus 7.75 square plus 3 square under the square root. And let's, for simplicity, let's assume that this magnitude is equal to d. So we can say that we can further simplify this. If I multiply this 60 inside with each and every component, so we can say 60x divided by d I. Similarly, since we can add this j component with the j component, so here we can say 60 into minus 7.75 divided by d. Let me write it like this. Initially we will have it like this. So 60 into minus 7.75 divided by d into j, and 60 into 3 divided by d into k, and this is that j term which comes in here. So this is 2 TAB. So we can add the j terms. So if we add the j terms, we can write it like this. This will become positive since we are taking out the minus sign. So we will add them like this, and then if we this will become as it is, and this, if I take this as an LCM, then we will have 120d plus 465. If I multiply 60 with this, so 120d plus 465 into j, and this is 3 into 60 is 180. So now this is RA, and similarly the this vector, which is the position vector of A relative to C, which will go from C to A, and we can simply find it if we start traveling from C towards A. So from C I need to travel 7.75 feet in the positive j, and then from there I need to travel 3 feet in the positive k, and the I component is 0. So this is 0I plus 7.75j plus 3k. This is the position vector of A relative to C. And similarly, since this is the mixed product, so we can find it, this will be mz, and since we know that the k unit vector will be, the k unit vector can also be written as 0I plus 0j plus 1k. So now we can write this dot product in determinant form, and that will be 0 0 1. This row represents that k, this row represents this vector, position vector of A relative to C. So we will write the components of this 0, 7.75 and 3, and this row represents the last vector, that is the resultant of the resultant force at A, which is 60x divided by d, this, and then minus 180 divided by d. So now if you find this determinant, you guys can see for this term I can hide this and this, so this and this multiply by 0. Similarly for this, this minus this multiplied by 0 becomes 0. So we can only write the determinant for this. So we can say this and this, we can hide this row, this, and 0 into this minus this. So we are only left with 0 into this 0. So 0 minus 7.75 into 60x divided by d, multiply by 1. So we are left with, basically we will have 1, 0 minus 7.75 into 60x divided by d. And this is equal to the magnitude of the moment about the z-axis, which is given, which is 279. So this means that 1 into 0, 0, and this will become equal to 279. So now let's simplify this. Let me erase all this and let me make it simple for you guys. So now if I cross multiply like this, is 279 divided by 1. So this goes, d goes there, and 279 comes in the denominator here. So we can write it like this. If we multiply both sides of equation with d and then divide both sides by 279, so the equation will look like this. And then if we simplify this, this is minus 7.75 into 60 divided by 279. This gives us minus 1.667 minus 1.667x equals to d, and we know that d is x squared. This is the d that we have assumed that this is equal to d, so that is equal to x squared plus 7.75 square. We can say this is equal to x squared plus 7.75 square plus 3 square under the square root. So in order to remove the square root, we need to take square on both sides. So this will cancel out, and we will have minus 1.667 square, which is equal to plus 2.778 x square equal to x square plus 7.75 square plus 3 square. And if I bring this x square to this side of equation, so that will become 2.778 minus 2.778 x square minus x square equals to 7.75 square plus 3 square, which will be equal to 7.75 square plus 3 square, 69.062. So this is 69.062, and this will become 1.778 x square equals to 69.062. And now since we want to find x, we can write it as 69.062 divided by 1.778 under the square root. So this is, we can say that square root 69.062 divided by 1.778, and this gives me x equals to 6.232 feet. So this is that maximum allowable x value, which will keep the moment about the z-axis magnitude equal to 279 pound-feet. So this is the solution of problem 350. I hope this will help you in your learning. Let me know in the comments if this helps. Do subscribe Engineers Academy for the solution of such more problems from Vector Mechanics for Engineers by Beer and Johnston.